Hello everyone, again welcome in this lecture. Today's our topic is Hamilton-Jacobi theory. This is the third lecture. In our earlier two lectures, in first lecture, we discussed about the canonical transformation. Then in the second lecture, we discussed about the Poisson's bracket. And today, in continuation with that one, we are going to discuss Hamilton-Jacobi theory. This is a very important theory in classical mechanics. So we are going to discuss today the Hamilton-Jacobi theory. Now in this Hamilton-Jacobi theory, let me share this slide. Yeah. Now, in this Hamilton-Jacobi theory, we are going to discuss the Hamilton-Jacobi equation. There are two photographs of two scientists or mathematicians. They have contributed in developing this particular theory. Sir William Rowan Hamilton, Irish mathematician. We know him about his contribution in mathematics and physics. Another one is Carl Gustav Jacob Jacobi, German mathematician. And both of them, they have contributed in developing the theory of Hamilton-Jacobi or Hamilton-Jacobi equation. In classical mechanics, the Hamilton-Jacobi equation, named after these two great mathematicians, gives an alternative formulation equivalent to other formulations such as Newton's law of motion, Lagrangian mechanics, Hamiltonian mechanics. Hamilton-Jacobi equation is also particularly useful in identifying conserved quantities for mechanical systems. So importance of Hamilton-Jacobi equation is it is identifying the conserved quantities. Now, another important point is it is very close to quantum mechanics. Interestingly, Hamilton-Jacobi equation is the only formulation of mechanics in which the motion of particle can be represented as a wave. It fulfills the aim of finding an analogy between propagation of light and motion of a particle. The wave equation followed by mechanical system is similar to but not identical with Schrodinger's equation, and also the Hamilton-Jacobi equation is considered to be the closest approach to classical mechanics to quantum mechanics. So it is the closest approach of classical mechanics to quantum mechanics. We have two different theories. One is a propagation of light and another is the motion of a particle. And that can be clubbed together by Hamilton-Jacobi equation. And that is the main object and that is the main achievement of Hamilton-Jacobi theory. Now, before coming to Hamilton-Jacobi theory and how the concept works, let us come to some beautiful pictures. And we are familiar with this type of process in our home. We go for shopping, particularly grocery shopping. And in grocery shopping, we have a large number of things to be purchased every week. And we bring those material in a trolley or in a bag to our home. So in a grocery, large number of eatable materials we purchase. And that can be divided into two parts. One, fruits and vegetables. Another, grain and pulses. So wheat, rice, etc. These are the grains. And fruits and vegetables are again a part of our daily shopping. So we segregate into two parts because fruits and vegetables, they do not stay long. So they have to be consumed and their freshness depends upon time. While grain and pulses, they remain preserved as it is for a long time. So pulses and grain do not spoil with time. So you can put it in a jar in our kitchen. But vegetables and fruits, they do not remain fresh for a long time. So these get spoiled with time. So there is a dependence of time. So we defined a function that purchase of fruits and vegetable, function f1, it is of x, x is the time dependent. And here the pulses and grains, they don't spoil with time. So it is a function f2 of y. Y is not time dependent. And purchase of grocery is a function of x and y because we purchase both of them. But when we bring it to the kitchen, we put them in a refrigerator in a different manner. And pulses and grains are again packed in a kitchen in a different manner. They put it in a jar or a bottles or any other containers. So we have a segregation, the material which is getting spoiled with time, so time dependent, and material which is not getting spoiled with time. So that is again, which is time independent. So we have two different type of materials. One is time dependent, another is time independent, and we are segregating into two parts. One is time dependent one, another is time independent one. This is the concept we are going to use in Hamilton-Jacobi theory. This is an important concept we are going to use in Hamilton-Jacobi theory, and that we are going to discuss in few more slides. Now we come to our today's topic, that Hamilton-Jacobi equation. Very simply, we are going to derive Hamilton-Jacobi equation. We can achieve that the new canonical variables represented by capital Q and capital P are constant in time by requiring that the transformed new Hamiltonian capital K will be 0. So if we consider capital K equal to 0, then Hamilton's canonical equation for new variables. So these are the Hamilton's canonical equation for new variables. And here we are considering K is equal to 0. So naturally this is also equal to 0. This is also equal to 0. Q dot I is also equal to 0. P dot I is also equal to 0. Now, according to the canonical transformation theory, the new Hamiltonian K and old Hamiltonian H are connected through generating function. We have already seen in our canonical transformation theory, in all the 4 equations, this equation was to be very common equation. So this is the relation between the new Hamiltonian and old Hamiltonian. So from equation 2, one can write very easily for K equal to 0 as follows, and generating function will satisfy with this particular equation. So H is the old Hamiltonian function of Q, P and T plus del F by del T, because K is equal to 0. So this is equation number 3. Now if we are taking generating function F as a function of old coordinates Qi and new momenta Pi, and time is common. That is why it is something like type 2 generating function F2. It is Qi, capital Pi and T. And then it is possible to write as following using the transformation equation for F2. So again, we remember transformation equation for F2 generating function. And this one of the transformation equation for F2 type generating function we have already derived in our earlier lectures. So Pi is equal to del F2 by del Qi. This is the transformation equation for F2. Now using equation 4 in our equation 3 and writing F equal to F2. So let us again go back. This is equation 3. Now we are substituting equation 4 in equation 3. So now H is a function of Q1, Q2, Q3 up to Qn, del F2 by del Q1, del F2 by del Q2, del F2 by del Q3 up to del F2 by del Qn T time plus del F2 by del T equal to 0. Now this is nothing but Hamilton-Jacobi equation. So derivation is very simple. Very simply we can derive Hamilton-Jacobi equation. Now Hamilton-Jacobi equation consists of partial differential equations. So these are the partial differential equations. there are n different equations over here and one more equation here. So there are total n plus 1 variables are there and n plus 1 partial differential equation. So n equation here and one more equation here. So there are n plus 1 different partial differential equations, and variables are q1 up to q1, q2 up to qn, and t is the last variable. Now, solution of Hamilton-Jacobi equation. So this is the differential equation. So the solution of Hamilton-Jacobi equation, which we have obtained in equation 5, is represented by function. It is represented by capital S, and that is called Hamilton's principal function or Hamilton's main function. So Hamilton's principal function is the solution of Hamilton-Jacobi equation. The integration of equation 5, let us go back. This is the integration of equation 5 because this is a differential equation. To solve that, we integrate it. So integration of equation 5 will give the dependence on old coordinates and time, but it will not inform how new momenta are within S. That is Hamilton's principal function. Mathematically, equation 5 is first order partial differential equation in n plus 1 variable. The solution can be achieved by taking integration, and the form is as follows. So f2 is equal to s function of q1, q2 up to qn, alpha 1, alpha 2 up to alpha n plus 1 t. Now here alpha 1, alpha 2, alpha n plus 1 are n plus 1 constants of integrations. So we know very well, whenever we try to solve differential equation, we try to integrate it. Whenever we integrate it, we have a constant of integration. So we have a n plus 1 partial differential equations. When we integrate it, we'll have a n plus 1 partial differential equations in integration, and then we have a n plus 1 constants. So alpha 1, alpha 2 up to alpha n plus 1 are n plus 1 different constants obtained after integration. This type of solutions are called complete solution of first order partial differential equations. So these are the first order partial differential equations. One constant out of n plus 1 constant is not relevant in this solution. We have a n plus 1 different constants. One constant is not important in the solution. Why? Because it is in an additive form. There are n constant in this particular form plus one constant that is due to the del f by del t. So one constant is in the additive form, and which is not important in the solution. Let us consider that if S is some solution of differential equation, and then S plus alpha is also solution where alpha is a constant. So S is a solution, then S plus alpha is also solution, and that is solution obtained after the integration process. If you revert it, then it is a differentiation process and we come to the original form. So if S is a solution, then if you differentiate it, you will get something. But S plus alpha, again you differentiate it. Alpha is a constant, and that constant differentiation becomes 0. So again, there is no change in the differential form. So that is why one constant which is in an additive form is not important and it can be omitted. So there is one constant in equation 6. In this equation, one constant which is a constant alpha tagged to S in an additive or a plus form and has no importance. So it is something like a S plus alpha form. So one constant is in the additive form or in a plus form, and which is not important and we can omit it. Therefore, the solution can be written as follows after removing that constant out of n plus 1 different constants. So now instead of equation 6, the solution becomes as function of q1, q2 up to qn, alpha 1, alpha 2 up to alpha n and t. Only difference is instead of alpha n plus 1, we go only up to alpha, and that is called equation number 7. Now, in that equation F2 is equal to S. We have already mentioned that it is a type 2 generating function. So F2 is equal to S. Again, S is a function of Q1, Q2 up to Qn, alpha 1, alpha 2 up to alpha n t. Now new momenta are constants. So we can write the new momenta Pi is equal to alpha I. So here all constants n are independent constant only. They are not in a additive form. Now we can write transformation equations as follows. So we are taking the transformation equations of F2 type. We have already mentioned that we are using F2 type transformation equation. We have also mentioned that we have taken F2 is equal to S. So whenever we write F2, we can equally write F2 is equal to S. So we can replace it by S. So we are using F2 type transformation equation. So we are knowing very well that in canonical transformation for F2 type generating function, this type of transformation equations were obtained. Now we replace F2 by S. So here it is replaced by S. Now Qi is as it is. Alpha I is in place of new momenta, because in previous slide we already mentioned that Pi is equal to constant, and that is new momenta. So Qi alpha it. And another transformation equation for capital Qi, delta del S Qi alpha int by del Pi, and here del Qi, and here del S Qi alpha it by del alpha I, and that is equal to beta I. Now using one process that is very popular in mathematics, that is the process known as turn inside out process, that is applied to equation 9 and 10. And that can be written as, now this was the part of the variable in the function. Now it has come as a main function. So Qi is equal to Qi alpha, beta, and t. So another one is Pi alpha, beta, and t. So earlier that was a part of the variable. Now that is a part of the function. And equation 11 are derived complete solutions of Hamilton's equation of motion. So we have used turn inside out process. So variables which were under the bracket, now they are part of the function. So that process is known as a turn inside out process. Now up till now we have obtained the solution of Hamilton-Jacobi equation. Hamilton-Jacobi equation is a partial differential equation, and we have obtained the solution. That solution does not tell us about the physical significance of Hamilton-Jacobi equation. It looks like a mathematics, but here we are going to see that what is the physical significance of Hamilton's principal function. Up till now we have defined Hamilton's principal function mathematics point of view, considering different variables. But now we are going to concentrate on physical significance of Hamilton's principal function, capital S. To find the physical significance of S, we take the total time derivative. So here is ds q alpha t by dt. Again, going back, this variables we are using qi alpha and t. So ds q alpha t by dt, taking total time derivative. So del s by del qi by del t, converting into partial derivative. Then alpha is a constant, so time derivative becomes 0. And again the last part is del s by del t. Now using equation 9 for pi. Now ds by dt summation, this becomes q dot I. Del qi by del t is q dot I. This is del s by del qi. Again going back, this is equation number 9. Here we have shown variable, but if we don't show the variable, del s by del qi. So here del s by del qi is represented by pi, and del s by del t as it is. Now going back to our equation 3. Now here equation 3 we have obtained by considering that U Hamiltonian is 0. So H plus del F by del T. Now we have considered in our solution of Hamilton-Jacobi equation that we have considered F is equal to F2. So again we can write F is equal to F2 in equation 3. Again we have considered that F2 is equal to S, that is Hamilton's principal function. So we can replace F by F2 again ultimately by S. So from this particular equation we can write H is equal to minus del F by del T. We can equivalently write minus del F2 by del T, or equivalently we can write del S by del T. And if we take negative sign on other side, so del F becomes del S by del T is equal to minus H. So here we can write del S by del T. So this is represented as Pi Q dot I minus H. Now again using Legendre transformation, we have already mentioned in the Legendre transformation, in transformation from Lagrangian to Hamiltonian, we use Legendre transformation. And here H is a Hamiltonian function, L is a Lagrangian function, both are connected by this particular formulation. So H and Lagrangian are related to each other through this formulation. Now we'll know that if you bring in this equation Lagrangian on this side, Hamiltonian on other side. So L is equal to Q dot I Pi minus H. So here Pi Q dot I minus H is nothing but Lagrangian. So in this equation ds by dt summation Pi Q dot I minus H is nothing but Lagrangian, and that is equal to dl by dt. So this is nothing but dl by dt. So if we write ds by dt equal to dl by dt, and if we want to find out the solution, we have to integrate it. So if we integrate it, integration is equal to S integration of Lagrangian L dt plus C. So integration becomes S equal to integration of Lagrangian dt plus C. C is a constant of integration. Now this gives the physical significance. We know that Lagrangian is a physical function of Qi, Q dot I and T. And it is equivalent to T minus V. So it is a physical quantity. Now this shows the physical significance of Hamilton's principal function. What we have derived, it can be mentioned as Hamilton's principal function S differs from the indefinite or infinite time integral of Lagrangian by a constant. So this is a integral of Lagrangian and constant. So S and integration of Lagrangian both are equal to each other. Only difference is plus constant C. So Lagrangian plus constant C is equal to Hamilton's principal function. Both are not equal to each other. Only difference is you have to add some constant, so it becomes equal to Hamilton's principal function. If both are equal, then constant should be 0. If constant C is equal to 0, then both are equal to each other. But if constant C is having some value, then both are not equal to each other. So difference is only equal to the constant. Now we come to another important part of the theory, and that is related with the Hamilton-Jacobi equation, and that is Hamilton-Jacobi equation for Hamilton's characteristic function. Now in this particular part of theory, we are going to use the separable variable technique or separation of variables. That is what we have seen in our first slide, where the purchase of grocery is divided into two parts. One which is spoiled with time, like fruits and vegetables. Another is not getting spoiled with time, like grains, pulses, and etc. So they are not getting spoiled with time. So one is time dependent, another is time independent. Same thing we do in mathematics. The process we are going in our day-to-day life in purchase of grocery is similar to the process we are doing in mathematics for separating two different type of variables. So here we consider that the function capital S or Hamilton's principal function can be separated into two parts containing coordinates q only and containing time only. So now we are dividing into two parts. One is time independent, another is time dependent. This type of separation of variables and integration of Hamilton-Jacobi equation is possible when the old Hamiltonian H does not contain time explicitly or clearly. In that case, the Hamilton-Jacobi equation can be written as, so this is Hamilton-Jacobi equation, del S by del T. Earlier we wrote del F2 by del T or del F by del T. We have already mentioned that del F is equal to del F2. Again, it is equal to del S by del T. And H in bracket Qi del S by del Qi equal to 0. The first term of this equation depends only on T. You'll notice that this is dependent only on T because T is in the derivative form. And the second term, S, depends only on Qi. So second term, that is depending only on Qi. So here only Qi, here only Qi. Derivative is in form of Qi. Here the derivative is taken with respect to time. Here derivative is taken with respect to Qi. So we have a separation of variables. One depending on time, another not depending on time. And that is represented as equation 30. By assuming the solution of time. So this is the type of solution we have assumed. S is a function of Qi, alpha I and T is equal to W, Qi alpha I and minus alpha 1T. Now this solution we have assumed. This is time independent part and this is time dependent part. Here you will not find any time. Here you will not find Qi. So again separation. Putting equation 14 in equation 13. So if you are putting this equation into equation 13 and performing differentiation. So you put wherever S was, you put W minus alpha 1T. So del by del T, W Qi alpha I, del by del T, alpha 1T plus in bracket Qi del W by del Qi is equal to 0. Now in this equation, in this particular term, there is no T. So differentiation with respect to T becomes 0. Here T is there. So differentiation will be minus alpha 1. And here it is with respect to del W by del Qi. So ultimately the equation will be minus alpha 1 plus this term. If you take alpha 1 on the other side, right hand side, this is the form of an equation. And that is equation number 15. So here alpha 1 is a constant. The time T is not involved in this equation. You will not find any time variable in this equation. There is no time. The constant alpha I appear in equation 1, appear in equation S. In equation, particularly S is the Hamilton's principal function where different constant alpha I appear. But only one constant alpha 1 is equal to constant value of Hamiltonian. So in Hamilton's principal function, different constant of integrations are there, alpha 1, alpha 2 up to alpha I. But out of them, only one constant alpha 1 is equal to constant value of Hamiltonian. So this shows that this is the Hamiltonian is equal to constant value of alpha 1. That is possible only for alpha 1. It is not possible for alpha 2, alpha 3, even for alpha I. Now we find particularly in canonical transformation approach. So again, we are using canonical transformation approach to verify this. We find that the time independent function W appears as a part of function capital S that is the Hamilton's principal function, and W separately generates its own contact transformation having properties different than generated by function S. That we are going to see that. Considering here a canonical transformation having all new momenta alpha I are constant of motion and alpha 1 is equal to Hamiltonian. So alpha I are constant of motion and only one constant alpha 1 is equal to Hamiltonian. If the generating function for such a transformation is W Qi, small qi, capital Pi, then transformation equations can be written as follows. Here we have taken new momenta Pi is equal to alpha I. And again, we are taking type 2 generating functions for transformation equations. So these are the transformation equations for type 2 generating function. So Pi is equal to del W by del Qi and Qi is equal to del W by del Pi. We can replace Pi by alpha I. These are similar to equations obtained for Hamilton's principal function for capital S. And that is equation number 9 and equation number 10. So these are similar to the equations we have obtained for capital S. Now the condition to determine W is H Hamiltonian is equal to alpha 1. Again, using 16. Now using 16 for substituting Pi. For Pi, we have to use equation 16. And Pi is given as del W by del Qi. So H is a function of Qi, del W by del Qi is equal to alpha I. And that is equation number 18. Now equation number 18 and equation number 15 are the same. Let us go back. This is equation number 15. And this is equation number 18. Both are same equations. So it suggests that the new Hamiltonian K is also equal to alpha 1. So both equations are same equations, and that says that the new Hamiltonian can be equated to alpha 1. Now we try to define Hamilton's characteristic function. The function W is known as Hamilton's characteristic function. In our previous slide, we have defined W. So this W is nothing but Hamilton's characteristic function, which generates a canonical transformation in which all new coordinates Qi are cyclic, and hence the conjugate new momenta Pi are all constants alpha I. So now W is known as Hamilton's characteristic function. Again, we take help of canonical transformation. And we consider that Qi are cyclic. All coordinates are cyclic. New coordinates are cyclic. And we already know that the conjugate momenta Pi are constant alpha I. So writing Hamilton's equation of motion for new system for Qi cyclic, all Qi cyclic. So P dot I is equal to minus del K by del Qi, and Qi cyclic, not part of the variables, so it becomes 0. And P dot I is equal to dPi by dt. So we can write Pi is equal to alpha I. So P dot I is equal to 0, that is equal to constant alpha I. Now, writing Hamilton's equations, here the new Hamiltonian depends only on new momenta, that is Pi equal to alpha I equal to constant. So we are writing Hamilton's equation of motion under the new system, Q dot I is equal to del K by del alpha I. And we know that for alpha equal to 1 or I equal to 1, alpha 1, I equal to 1, it is Hamiltonian. So del K by del H. Alpha 1 is equal to Hamiltonian, that we have already seen in our last slide. But not other alphas. Alpha 2, alpha 3, alpha I, they are not equal to Hamiltonian. So we have put the condition that I is equal to 1. So it becomes del alpha 1. Then alpha 1 is equal to Hamiltonian. And again, we have mentioned that old and new Hamiltonian are same. So del K by del H becomes del K by del K and is equal to 1. But if alpha is not equal to 1, but alpha is equal to 2, 3 up to alpha I. So here it is mentioned I is not equal to 1. Then this cannot be written and Q dot I is equal to 0. So that is equation 20. The solution of equation 20 is obtained by integrating, because this is dq by dt and that is equal to 0, that is equal to constant. So if you want to integrate it, so it is q1 equal to t plus beta 1. Beta 1 is a constant of integration, equal to del w by del alpha 1 and del w by del h. And here alpha 1 is equal to h. There are two equations. For first equation, we can write like this. That is, for the second equation, qi is equal to beta I del w by del alpha I, because here I is not equal to 1. And the upper condition is I equal to 1. And we obtain this particular type of relation. The only coordinate q1 is constant of motion and also equal to the time plus constant beta. So if we have I equal to 1, then we have this type of derivation. And q1 is a constant of motion and equal to time plus beta 1, or a constant of integration. Here another conjugate relationship between the time as a coordinate and Hamiltonian as its conjugate momentum is obtained. Now here we have one conjugate relationship. Q1 is equal to del W by del H. If you forget about the in-between thing, then it becomes Q1 equal to del W by del H, omitting in-between thing, because this is equal to this is also equal to this is also equal to this. So Q1 can be considered as equal to del W by del H. And if we remember our conjugate relationship, either coordinate or momenta is related to coordinate or momenta through Lagrangian or Hamiltonian. That is the definition of a conjugate variables. So here coordinate is there. In place of momenta, we have a W over here and we have a H over here. So in place of Lagrangian or Hamiltonian, we have a W. In place of the momentum or coordinate, we have a Hamiltonian. So we have one more conjugate relationship there. The time is a coordinate and Hamiltonian as its conjugate momentum. So here Q1 is equal to T plus beta 1. This is a constant. So time is a variable. It is equivalent to coordinate. This is the equivalent to momentum, and this is equivalent to a function. And that function earlier we had a Lagrangian or Hamiltonian function. So we have a new conjugate relationship where the time is something like a coordinate and Hamiltonian is something like a momentum, and W is something like a Lagrangian or Hamiltonian. So this is the new type of conjugate relationship we have obtained. Now we are coming to one more important quantity, and the title is action of the system. Taking total time derivative of Hamilton's characteristic function W. So here we have defined W. W is a function of Qi alpha I. There is no time. But if we take a total time derivative, it is possible to take a total time derivative in terms of a partial time derivative. If we consider that it is independent of time, but if we take a total time derivative, mathematically we can split into partial derivatives. So here we are taking a total time derivative. dw by dt is summation I del w by del qi by del t, and Del alpha by del t, alpha is a constant, so it is 0. Now this can be represented as q dot I, because del qi by del t is q dot I, and this is from again earlier equation we can represent it by pi. So we have mentioned here using 16, we can represent this del w by del qi as pi and del qi by del t as q dot I. So this looks to be a time independent, but total time derivative can be taken by considering that for a short time period it is independent of time, for a long time period it is slowly varying with time, and we can take a total time derivative which is split into the partial time derivatives. Now dw by dt becomes summation pi q dot I. That can be solved by integrating. So it is w integration of summation pi q dot I dt and q dot I dt. So q dot I is dq by dt, and that is again dt cancels out. So we have an integration of summation I pi dqi, and that is equation number 22. So equation 22 is known as the action of the system. For simple harmonic oscillator, the action of a system is represented as W equal to integration P dq. And that is represented by equation 23. This shows the area of ellipse, and that is twice pi E by omega, and is a constant quantity. Classically speaking, the oscillator can be given oscillations with any amplitude, and E, the energy, can change continuously. So in a classical oscillator, the energy changes continuously. But in quantum mechanics, the action of the oscillator is quantized quantity. So we have to apply the quantum conditions to this particular action. And interestingly, in our undergraduate level, after Bohr atom model, we have used Sommerfeld atom model. In Sommerfeld atom model, this was the starting place. This was the starting point. We started our derivation by considering first this particular equation. And there we consider elliptical orbit. So there we used this also. So this is the starting point of Sommerfeld atom model. So we want to emphasize here that classical mechanics was developed long back and quantum mechanics was developed later on. But there is a close relationship between classical mechanics and quantum mechanics. And many times the beginning in quantum mechanics is taking place with a formulation derived from classical mechanics. Now, I want to share one very interesting thing. Before your birth, most probably you all are between 21 and 20 years of age. I wrote this article, popular article, on Sir William Rowan Hamilton, a prodigious personality of last century. And that was written by myself and my wife. She's also a physicist. So we both wrote this article, and that was written in 1992, long back, before your birth. And this is the volume number, and these are the page number. I have put the photocopy of the first page. There we have briefly mentioned about the biography of Sir William Rowan Hamilton. And there we have mentioned that he was doing 13 different languages at age of 14. And those languages like Persian, Arabic, Sanskrit, then Syriac language and Bengali and like that, many languages he was doing. So he was a very intelligent person. He was a great mathematician, but also a great linguistic also, knowing many different languages. So here I wanted to share this information. Also, I share that for further reading, the classical mechanics by Goldstein, one can refer for further reading. So the last slide is a thank you. And this is a beautiful picture surrounding Rajkot only, nearby Khirasra village. You will find beautiful hills with lush green grass. It's a grassy land. So it is a beautiful picture of a sunset nearby Rajkot. And during weekend relaxation, I prepared the slides. So again, I want to thank you during relaxation. So thank you very much for patient hearing, and thank you very much. And again, I will go further in our classical mechanics lectures. So thank you very much. Thank you very much.